Okay, let's do problem 3. Find a geometric power series for the function centered at 0. All right. So geometric power series, I'm going to my formula sheet or my textbook, and I'm going to say, well, geometric power series, I know those. That looks like this, right? This power series can be, the sum is given by this formula provided that r is less than 1, absolute value r less than 1, right? We learned that way back when we were looking at series before we got into series as functions, okay? So how can I use this to find a power series for this guy? Well, um, I need to rewrite this thing, right? The idea is, let me show you your book's logic here. Um, and by the way, I'm going to make your final open book. So I want you to use your textbook, but not, of course, you can't just start Googling stuff, but your book will be a guide. And if you want, you can put, also allow you to have a card, like a big index card, 5x8 index card, and you can put all your formulas on it. There's a lot of formulas in this course, right? Especially for this chapter 9, we got to lean on our book. For example, when it says this question, find a geometric power series, I'm saying, okay, geometric power series, what's that? That's this thing. All right, how do I put this problem in this form? Okay, so in your textbook, the concept, um, geometric power series. So the idea here, let me close that guy. Um, so any function that looks like this, f of x equals 1 over 1 minus x, looks a lot like the result of the sum of geometric series, a over 1 minus r, right? So the idea here, and remember, we've shifted from the result of a sum of a series to functions. We got an x now, right? So the idea here is that we say, well, if I have something that looks like this, I can go this way, right? So I want to put my given function into this form, and then I can come up with a series for it. All right, so that's the idea. So let's try and do that for this problem number 3. Okay, so we got to do a little bit of algebra. So this guy would be, all right, I need a 1 here, and I need a minus here. Start with the denominator always. So I'm going to divide everything by 2. 3 over 2. 2 over 2 is 1 plus x over 2, right? That's the same function if I just multiply the numerator and denominator by half. And then I need that to be a minus. Well, that's easy to do because we know that plus is a double negative, right? We can bring that in. All right, so now I can apply this. I have a equals 0 to infinity. A is my numerator, 3 halves. R to the n, what's r? It's this value here. And that's it. That's my geometric power series. All right. However, we could probably clean that up. That's going to be an alternating series, right? So usually we like to pull out the alternating part. That's -1 times x to the n. So I have a -1 to the n times x to the n. All right. That's my numerator. And there's a 3 in there. We can put him right there. That's not raised to any power. Sorry, that's a little messy. Clean that up a bit. Times 3x to the n. It's a little bit better. And then my numerator, it's a 2 to the n and another 2. So I could clean that up. 2 to the n times 2 is 2 to the n plus 1. Okay. It's all about figuring out which to use. By the way, so for the next one, for example, find the sum of a convergence series by using a well-known function. If you see something like this on your file, say, oh, well-known function series. Well, I got a list of those, right? So hopefully you're referring to your book, but let me show you the list. Here it is. So this is a list of all your Taylor series. So I can expand it. And these should look familiar because you've been working with them, right? You got the natural log, you got e to the x, 1 over x plus 1, uh, 1 over x, sine and cosine, definitely. These three are real common. Also, the 1 over 1 plus x you've seen a lot. So a lot of times, instead of like redoing these all together, we say, okay, I know what the I know what the power series is for e to the x. It's this, right? And I can just use that if I'm dealing with some kind of transformation of that, right? So when I see this problem, find the sum of the convergence series by using a well-known function. Okay, well-known function, that means what does this most look like? How can I manipulate this thing so it looks like something that we've done before? One of those well-known functions. Well, to me, it's I got n factorial and I got a power of n. That there's two n's. There's one in the numerator and denominator, so that's a little confusing. But with a little bit of manipulation, a lot of algebra and calculus, right, and we do this kind of stuff a lot in here, I can think of it like that. And I say, well, that looks like x to the n over n factorial, where x is 2/3, right? X to the n over n factorial, that sounds familiar. That's my e to the x function, okay? So I guess the question is, what would my other options be? If you don't see that, what else do you have? Well, here's your formulas, right? 2n factorial for cosine, 2n plus 1 for sine. Looking at the denominator, I think it's a pretty straightforward option in terms of our well-known functions. The problem is if you miss it, then there's nowhere to really go with it, right? So you really got to say, well, okay, that looks a lot like e to the x. So that's going to just be, and then we're done, right? Because x to the n over n factorial is the series representation of e to the x. Right, so how about that? That we found this infinite sum just by recognizing something, a result we already had, and then we were able to evaluate e to the 2/3, which is somewhere around 2.